Hello and welcome to week 6 of this course, Fundamentals of Semiconductor Devices, being taught by Professor Digvijay Nath. Course ID is NOC 25E39. Little about me. My name is Mayank Goyal and I am a research scholar at the Department of Electrical Engineering, IIT Bombay. About this course, it is being taught by Professor Digvijay Nath, who is a associate professor at ISC Bangalore. The course plan for this week is BJTs, their working principle, their parameters, current components, then their base transport factor, early effect, charge control equation, current gain, need for HBTs, then applications in real life, things like that. So this session, this live session typically happens on Sunday 6 to 8 p.m. But due to some reasons this week, it is happening today on Tuesday 3 to 5. And this is the Google Meet link. So like always, we will do some practice questions that will help you better understand this week's topics, as well as the have you give you some ideas about the questions. So the first question is, what does BJT stand for? Bipolar junction transistor, binary junction transistor,
A. Answer A.
bias junction transistor, and basic junction transistor. So the answer is A, bipolar junction transistor. Next question. How many PN junctions does a bipolar junction transistor BJT have? 1, 2, 3, 4. So you know how many are there?
Sir, NP, NPNP. Yeah, PNP.
Yeah, so the answer would be 2. So if you see NPN, so there is an NP and a PN. So it has two junctions. Similarly, PNP, it has a PN and an NP. So two PN junctions in a BJT has two PN junctions. Next question. What does bipolar in bipolar junction transistor signify? A. The transistor has two separate charge carriers, electrons and holes. The transistor can operate in two modes. It has two PN junctions. It requires two voltage sources.
D.
The correct answer would be A. The transistor has two separate charge carriers, electrons and holes. So the working of a PN junction is basically a BJT. It involves the conduction of both the electrons and holes. Therefore, the term bipolar. So you see, electrons are negatively charged, holes are positively charged. So they are opposite poles. So therefore, the term bipolar comes. So a PN junction is called a bipolar junction because when a PN junction is forward bias, it has conduction from both electrons and holes. Therefore, a PN junction is called a bipolar junction, and a BJT is made from PN junctions. Therefore, it's called a bipolar junction transistor.
If you, it would be NPN, sir. Then what happens?
Does not matter if it's NPN or PNP. So a PN junction is a bipolar junction, and this is a transistor made from PN junctions, multiple PN junctions, so two PN junctions. Therefore, it's called a bipolar junction transistor. Basically, a bipolar junction transistor means a PN junction transistor. Bipolar junctions means a PN junction. So it is a transistor made from bipolar junctions.
Okay, sir.
What is the primary function of a BJT? Convert AC to DC, amplify current and voltage, store electrical charge, rectify signals.
B. Answer B.
Yes, the answer would be amplify current and voltage. So the purpose of a BJT, typically it has mainly two purposes. One is to act as an amplifier, and second is to act as a switch. A switch is basically it has two states, an on state and an off state. In on state it will conduct, and an off state it won't conduct. And then amplifier, basically you have a signal, current signal in the input, and at the output you will have an amplified signal. That means if it's in microamperes you will have in milliamperes and such that. So when it comes to switching, there are better devices than a BJT, but for amplifying, BJT is the best device. I, bipolar junction transistor BJT consists of which three regions? Source, drain, gate, anode, cathode, base, emitter, base, collector, gate, substrate, drain.
Answer C.
That is correct. The answer would be emitter, base, collector. So, which region in a BJT is the thinnest and lightly doped? Emitter, base, collector, both emitter and base.
B, sir.
That is correct. The answer would be base. So you want the base to be the thinnest and lightly doped so that there is less amount of recombination. What is the correct biasing condition for a BJT to operate in the active region? Both junctions are reverse biased. Both junctions are forward biased. Emitter base junction is forward biased. Base collector junction is reverse biased. Emitter base junction is reverse biased. Base collector junction is forward biased.
Answer C and D, sir.
No, it will be either one of them.
C.
The answer will be C. So the emitter base junction will be forward bias, so that you will have charge carriers going from emitter to base, and then base collector would be reverse bias, so that you have less number of recombination happening, and there will be a minority carriers going into the collector. In a BJT, the majority carrier type in a base of an NPN transistor is electrons, holes, ions, both electrons and holes.
D, sir.
So the answer would be holes. So it's an NPN. So you have N type emitter, P type base, and N type collector. So your base is P type. So in P type semiconductors, you have studied that the majority carrier is holes. Therefore, the answer for this is holes. Which BJT configuration provides the highest voltage gain? Common base, common emitter, common collector, emitter follower.
D, sir.
That is correct. The answer would be common emitter. So in common emitter mode, you connect your emitter to your base as well as your collector terminal, and so collect it can give electrons to both your base and your collector. Which of the following statements about BJT current components is incorrect? Emitter current is the sum of base and collector currents. Base current is very small compared to collector current. Base current is primarily due to recombination in the base. Collector current depends significantly on collector voltage. Which of these is incorrect?
See, sir.
So the answer to this is actually D. Collector current depends significantly on collector voltage. So your by Kirchhoff's law, since your we just stated that our configuration is common emitter configuration. So in common emitter configuration, if you apply Kirchhoff's law, you will get that is emitter current is due to current from both base and collector. So it is sum of both base current and collector current. And base current is very small compared to collector current. That is how your amplification works. The base current is primarily due to recombination in the base. So the since it's a lightly doped, it has a significant depletion region, and there a recombination is happening, which is the result of base current. So the wrong answer is collector current depends significantly on collector voltage. So that is actually wrong. If you see the IV characteristics, you will see that in the active region, your collector current is constant. It's it's independent of your collector voltage. It is only dependent on your base current. Why is the collector region larger in a BJT? To accommodate more doping, to dissipate heat efficiently, to reduce recombination, to increase the base width. Why is
D,
the
sir.
answer to this would be to dissipate heat efficiently. Since collector current has a high collector region has a high current, so it will very it will generate more heat. So we make it so it's made very large region so that we can dissipate that heat. So this is a numerical simple. A BJT has a current gain beta of 100. If the base current is 50 microamperes, what is the collector current? 5 milliamperes, 50 milliamperes, zero point 0.5 milliamperes, or 10 milliamperes? This is a very simple question.
See, sir.
So you are saying the answer is 50 milliamperes. So the answer to this is actually 5 milliamperes. So your gain is given by your collector current divided by your base current. So your collector current would be beta into base current. So 100 into 50 microamperes, which would be 5 milliamperes. So 5000 micro is your 5 milli. Next question. For a silicon BJT, if the base emitter voltage drop is 0.7 volts and the base current is 20 microamperes, what will be the emitter current given beta equals to 50? 1.02 milliamperes, 1.02 microamperes, 0.98 milliamperes, 0.98 microamperes. So anyone able to get the answer? So the answer to this is A, 1.02 milliamperes. So you can calculate the collector current using beta IB, which would come out to 1 milliamperes. And we just studied that your emitter current is sum of base and collector current. So you add 1 milliampere plus 20 microamperes, you will get 1.02 milliamperes. Now this is just similar question but reversed. Now you have a transistor has a emitter current of 5 milliamperes and a base current of 50 milliamperes. What is the current gain beta? 90, 99, 100, 101.
D, sir.
That is correct. The answer would be 99. So you can calculate beta by using IC by IB, and IC you can write as IE by IB. Now you know all the values. So you substitute them 5 milliamperes, 50 microamperes by 50 microamperes, and you solve it, you will get 99. A BJT has an emitter injection efficiency gamma E of 0.98 and a base transport factor B of 0.99. What is the current transfer ratio alpha? 0.9702, 0.9800, 0.9990, or 1.000?
See, sir.
Answer you are saying is 0.98. The answer to this is actually 0.9702. So your current transfer ratio is given as product of your emitter injection efficiency and your base transport factor. So that would be 0.99 into 0.98, and that comes out to be 0.9702. Next question. If a BJT has a current transfer ratio alpha of 0.98, what will be its current gain beta? 48, 49, 50, 51.
B, sir.
Yes, the answer would be B, 49. So beta is given by alpha upon 1 minus alpha. So you substitute that and you will get 49. What does the nearly constant region of the collector current represent? Ohmic region, active region, cutoff region, breakdown region. So in an IV characteristic curve of BJT, what would be the nearly constant region of collector current? So the answer would be active region. So in active region, the collector current is constant. It does not depend on the collector voltage. So a Darlington pair consists of two MOSFETs in parallel, two BJTs connected for high gain, a BJT and a MOSFET, a single transistor with higher resistance. So the answer to this would be two BJTs connected for high gain. So you know a BJT is an amplifier. So you connect the output to of one BJT to the input of second BJT, and the so you can have multiplication of your a- amplification of your amplification. So it will be double amplification, not double. It will be multiplied. So like 100 into 100, you will have an amplification of 10,000. Which factor primarily represents the current gain beta of a BJT? Primarily determines the current gain beta of a BJT. Emitter doping level, collector voltage, base recombination rate, emitter base voltage. The correct answer for this is base recombination rate. So your current gain is collector current divided by your base current. So if your base recombination rate is higher, your base current will be higher, and that means the electrons that it is taking from the emitter is it is not giving it back to the collector. So your collector current will also will less. So overall, your current gain will reduce if your base recombination rate is higher. In an IV characteristic curve of BJT, in which region does the transistor behave like an open switch? Active region, saturation region, cutoff region, breakdown region. Yes, the answer to this is C, cutoff region. So in cutoff region, your base emitter junction is also reverse bias. So if your base emitter junction is reverse bias, your emitter current is not going towards your emitter current is not going to your base, which does not, which means it will also not go to your collector. So at this point, your since both of your transistors are reverse bias, there won't be any current conduction. So it will act like an open switch. So what is the condition for the transistor to be in cutoff? VB greater than 0.7 volts, VB is less than 0.7 volts, VC greater than 1 volt, IC greater than IE. So your answer to this is VB less than 0.7 volts. So you know typically in silicon PN diodes, your knee voltage is around 0.7 volts. So below 0.7 volts, you won't have any current conduction. So your device would be in cutoff region. So only after maybe 0.7 volts, you will have current conduction and device will work.
Sir, please repeat again, sir.
So in if you remember from your previous classes in silicon PN diodes, your knee voltage where your diode starts conducting is 0.7 volts. So if since your this is your base emitter is your PN so here we are talking about silicon devices. So for a silicon PN junction, your knee voltage is 0.7 volts. So below 0.7 volts, you won't have any conduction. So similarly, in this case, your base emitter. So you want current conduction through your base emitter junction. So for that, your VB should be greater than 0.7 volts. Otherwise, you won't have any conduction and your device will be in the cutoff region. So if you have a silicon BJT, you need VB greater than 0.7 volts to have current conduction through your base emitter junction. Your base emitter junction will then be forward biased and have a current conduction, and then only it will give current. It will show current at the collector region, and your device will be will act as a closed switch. That will start conducting current. What is the primary reason for keeping the base width of a BJT small? To increase the base resistance, to reduce base recombination and improve current gain, to increase the breakdown voltage, to allow more holes to diffuse into the emitter. So the answer to this is to reduce base recombination and improve current gain. So if your base width is very small, your there won't be much diffusion region in the your diffusion region will be larger than your BJT base width, and there won't be much place for recombination. And if there is not much recombination, the carriers that are coming from emitter to your base will go to your collector. They will not be lost in recombination, and you will have better you will have lower IB and higher IC, and that will improve your current gain. In an NPN transistor, what happens if the base doping is significantly increased? The current gain increases, the early effect becomes more pronounced, the base transport factor decreases, the collector current decreases. So the answer to this is actually the base transport factor decreases. So if your base doping increases, your recombination rate will increase. So current the current from your base to your collector will decrease. So your base transport factor determines how much current is going from your base to your collector, and that will decrease because of higher recombination. What is the impact of increasing the emitter doping in a BJT? Increases the emitter injection efficiency, decreases the base transport factor, reduces the early effect, decreases the collector current. Yes, the answer to this is increases the emitter injection efficiency. So if you increase your emitter doping, so it will be able to inject more electrons into the base. So your emitter injection efficiency will increase. So, and we just studied that your gain is dependent on your current trans transfer ratio, and your current transfer ratio is product of your emitter injection efficiency and your base transport factor. So if you increase your base doping, your gain will decrease. If you increase your emitter doping, your gain will increase. But which of the following is a practical limitation of increasing the emitter doping excessively? Reduced breakdown voltage, increased recombination in the collector, loss of transistor gain, reduced collector current. So the answer to this question is loss of transistor gain. So we just studied if you increase the emitter doping, your transistor gain will increase. But if you increase emitter doping very high, so you will have you will see the start seeing the effect of your dope excess carriers, and you will have a degenerate semiconductor, which means your band gap will start narrowing, and that will impact your current transfer, and it will lead to loss in transistor gain. So there is a limit to emitter how much doping you can have at your emitter. What is the early effect in a BJT? Increase in base width due to high collector emitter voltage, decrease in base width due to high collector emitter voltage, increase in emitter doping due to forward biasing, reduction in collector current due to base widening. So the answer to this is decrease in base width due to high collector emitter voltage. So if you increase your collector emitter voltage to a very high value, it will lead to a bigger depletion region in your base since it's a very less dope, and due to a widening of your depletion region, your base width will decrease, and if your base width decreases, your recombination will reduce and your gain will increase. So your collector current will start getting instead of showing a flat region, it will become dependent on your collector emitter voltage, and you will see a slope in your output characteristics where your collector current will increase with your collector emitter voltage. How can base width modulation early effect be minimized in a BJT? Increasing emitter doping, increasing base doping, reducing collector voltage, increasing base width. So the answer to this would be increasing base doping. So if you increase your base doping, your depletion region will be stronger, and it will be less affected by your high collector emitter voltage. But this is a trade-off, as if you increase your base doping, your recombination rate will also increase, and your hence your transistor gain will decrease. So you have to have a balance between the doping and your early effect to have an optimal device. Next question. What does the Gamal number G in a BJT represent? The total number of charge carriers in the base, the total amount of dopant atoms per unit area in the base, the mobility of electrons in the base, the ratio of emitter to collector current. So your answer to this question would be the amount of total amount of dopant atoms per unit area in the base. Sir, Gamal number is a representation of your doping density, areal density of your doping, dopant atoms per unit area. So now some numericals. A BJT has a base width of 0.5 micrometer and a diffusion length of 5 micrometer. What is the base transfer factor B? 0.96, 0.99, 0.98, 0.97. So the answer to this would be B 0.99. So your base transfer factor is given by 1 minus your square of WB by Ln, so where WB is your base width and Ln is your diffusion length. So if you substitute the values here, you will get 0.99. So you can see your WB is your base width and your Ln is your diffusion length, which is dependent on your doping. So a higher doping would mean your a smaller diffusion length, which will reduce your base transport factor. So for best base, so have your best base transfer factor, your base width should be less and your doping should also be less, so that your diffusion length is higher. Next question. A BJT has a Gamal number G equals to 10 raised to power 12 per centimeter square. A base collector depletion width WBC of 1 micrometer and a base doping NB of 10 raised to power 17 per centimeter cube. What is the approximate early voltage VA? 10 volts, 50 volts, 100 volts, 200 volts. So the answer to this would be 100 volts. So your early voltage can be calculated from G divided by NB into WBC. So all three are given to you. You substitute 10 raised to power 12, NB 10 raised to 17, and WBC in terms of centimeter is 10 raised to power minus 4. And you calculate, you will get the answer to be 100. What is the primary cause for delay in a BJT? Low emitter doping, carrier recombination in the base, space charge transport in the collector, the presence of parasitic inductances. So the answer to this is carrier recombination in the base. So a higher amount of carrier recombination will lead to more delay in the transfer of electrons from transfer of carriers from your base to collector, and that creates a delay. The cutoff frequency ft of a BJT is the frequency at which the collector current becomes independent of base current. The current gain becomes 1. The transistor enters saturation mode. The base collector junction becomes forward biased. So the answer to this is the current gain beta becomes 1. So as you increase the frequency of your BJT, you will have less and less time for your current to go from your base to your collector, and that will cause a decrease in your current gain. So at a particular frequency, your current gain will become 1, and if you go to a higher frequency, your current gain will become less than 1, and at that point, your instead of becoming an amplifier, your BJT will start acting as a damper. That will it will start the output current will become less than your input current. So that means your BJT cannot be operated at a frequency higher than this frequency, and therefore it is called a cutoff frequency. Which factor has the most significant impact on the BJT cutoff frequency FT? Collector voltage, base transport factor, transit time of charge carriers, base width modulation.
Yes, sir.
So the answer to this is actually C, the transit time of charge carriers. So the higher your transit time would be, the lesser your cutoff frequency would be. So you want your transit time to be as low as possible. So and transit time would depend on multiple factors such that your base emitter junction, your recombination rate in your base, and your base collector junction. Which technique is used to increase the cutoff frequency of a BJT? Increasing the base width, reducing base transit time, increasing base recombination, using a lightly doped emitter.
See, sir.
That is correct. The answer would be B. reducing base transit time. So as we discussed just now, the higher, the lesser the transit time, the higher would be your cutoff frequency. So by and how can you reduce your base transit time? The best way is to reduce the recombination in the base, which can be done by either smaller base width or lesser doping. Next question: heterojunction bipolar transistors (HBTs) improve speed by a increasing base doping, reducing emitter base capacitance, using different materials for the base and emitter, increasing base widths. So the correct answer for this would be using different materials for the base and emitter. So in normal BJTs, all your three regions are your silicon, but in heterojunction, you can have different materials. Like you can have a metal instead of your silicon for your emitter, or you can have a higher band gap material such as germanium instead of silicon, such that your base your base emitter depletion region will reduce, and that will increase the transit time across your base emitter region. So by improving their transit time across the base emitter junction, you will have higher speed. Now some so if your emitter material is metal, your depletion will so it will lead to a higher depletion width. So it will lead to narrowing of higher depletion widths in your base because it's a Schottky junction, and so your base width will reduce. So your beta should increase. I am not sure about that, but I think your beta should increase if your emitter is a metal. But I am not sure about that. So next question. A BJT has a total delay tau of 10 picoseconds. What is its cutoff frequency FT? 5 gigahertz, 10 gigahertz, 15.9 gigahertz, 31.8 gigahertz. That is correct. So the answer would be 15.9 gigahertz. So your FT is given by 1 by 2 pi tau. And if you put tau as 10 picoseconds and you solve, you will get 15.9 gigahertz. A BJT has a collector-based depletion width WBC of 0.5 micrometer and a carrier velocity of 10 to the power 7 centimeter per second. What is the transit delay across the collector junction? 5 picoseconds, 10 picoseconds, 25 picoseconds, or 50 picoseconds?
Answer A.
That would be correct. The answer would be A, 5 picoseconds. Your transit delay across junction would just be your depletion rate divided by carrier velocity. And if you put the values, you will get 5 picoseconds. Next question. A BJT has a base width of 200 nanometer and an electron diffusion coefficient Dn of 25 centimeter square per second. What is the base diffusion delay? Tau b. 8 picoseconds, 16 picoseconds, 32 picoseconds, 64 picoseconds.
Yes, sir.
So your answer to this would be actually A, 8 picoseconds. So tau b is given by WB square by 2 dn. And if you put the values there, you will get 8 picoseconds. So these are the questions I have for today. Thank you for listening. If you have any doubts, you can ask.
Sir, how cutoff voltage happen?
What?
Cutoff voltage. Cutoff voltage.
Yeah, so cutoff voltage is your basically your so for your region to be in for your device to be in cut off, basically it means that your device is not conducting. There is no current flow through your device. So and we just saw that typically in BJT, your base collector is reverse biased and your base emitter is forward biased. So a typical current flow in your BJT is your electrons come through your emitter. So, so your current goes through your emitter to your base, and from base it goes through your collector as a minority carrier current. From emitter to base, it is a majority carrier current. So, if you want to put your device in cutoff, you want to remove the current that is going from emitter to your base. That means you want to stop the conduction of current at your emitter base junction, and the current conduction in a PN diode only happens above the knee voltage. If you plot your current versus voltage, you will see till knee voltage your current is almost negligible, and after that it shoots up. So, and for a silicon PN diode, your knee voltage is approximately 0.7 volts. Hence, if your VBE is less than 0.7 volts, you won't have any current going from your emitter to your base, and Therefore, there won't be any current conduction. So your device will act as an open switch. Therefore, it is called cutoff region.
Okay, sir.
So if you see this question, your base transport factor is given by 1 minus WB by ln whole square. So and ln you know is under root of tau and tau dn. So in your question, your dn is given as 100 centimeter square per second and your tau is given as 10 nanoseconds. From this, you can calculate your diffusion length ln and your WB here is given as 5 micrometer. So if you put all these values here, you can calculate your base transport factor. So you, in your question, you are given dn and tau. Using dn and tau, you can calculate your ln and then you can use this formula to calculate your base transport factor. So you can just replace your ln by your diffusion length formula. Yes, this is the formula 1 minus W by L square.
Hello, hello. Am I audible? Good evening, sir.
Good evening.
Sir, I'm asking that the formula we used 1 minus WB square upon ln square. So in the lecture, sir, the written formula is 1 minus Wn upon 2 into ln square.
Yeah, so use that formula then. Don't use the formulas that are given to you in the lecture videos.
But I'm getting different answer from your formula and from the sir's given formula.
Yeah, it will be different answer because formula is different. So I am not telling you to use the formula that I have shown. Use if you can if the formula in class is different, then use that formula. Don't use my formula. I am I am
Yes, sir.
so the formulas can be different depending on the ideality factors of also like
Both questions are same, sir. Only the formula there is to multiply factor of 2 in ln.
yeah, so sometimes the formulas can be a little different depending on the ideality factor. There is so there is so not a every transistor is not an ideal transistor, right?
Yes, sir.
So these formulas are are not like these formulas came from experimental values. So
Yes, sir.
so there might be discrepancy in the formulas. So the answer that you will get will be the questions that you will get will be based on the lecture videos, not the slides that I am showing or anyone else is showing. In the assignments and exams, the questions will depend on the lecture videos.
Okay, sir.
So use the formula that you can see in the lecture video.
Oh. So can I share my screen? I have some question.
Can you share?
No, sir, I'm not able to share.
I think now you can share.
Oh, sir. This is visible, sir.
Yes.
So I'm asking for the sir. What is the sorry? What is the cutoff frequency for this graph, sir?
See, I know you are asking me assignment questions, but I am not allowed
I'm
to
asking only for and say
I am not allowed
not
to
an
give
answer, sir.
answers to your assignment question.
Asking for doubts and that is what is the cutoff frequency for that? How can I find the cutoff frequency? There is a question for delay, not the frequency.
So you have to convert your gain into your this. So the cutoff frequency is the point where your gain is one.
So gain is one on magnitude of zero, right? Log one is equal to zero.
Yes,
So the what will be frequency, sir, here, right?
you can calculate from the graph, right?
It is difficult for me, sir. Can you help?
your 0 point and like it matches with, how can I show you, like if you see after 10 is to power 5, you can see, can you see
Yes,
the
sir.
lines
Yes,
going
sir.
here?
It's yeah, there.
Yeah, so this will be your value. And
So I think it's 10 in the multiply factor of 10 to power 5, right?
yeah, so this is in log scale. So this is,
Oh,
so this is like 10 is to power 2. Then no, so you start from the, yes, so you start from the bottom value. So this would be 1 into
yes, sir.
10 is to power 2. This will be 2 into 10 is to power 2. 3, 4, 5, 6. This will be 9 into 10 is to power 2. Next would be 10,
Yes,
1 in 10 into 10 is to power 2, which is your 1 into 10 is to power 3.
yes,
Now,
sir.
now you repeat again, but so this will be a 2 into 10 is to power 3. So here, so that here it is 9 into 10 is to power 3. Then this would be a 10 is to 10 is to power 3, and which will becomes your 10 is to power 4.
Yeah.
So similarly, you can calculate the value for here.
So it is 10 into 10 to power 5.
No, this value is 10, this is like this is 1 into 10 is to power 5, and this is 10 into
Oh,
10 is to power 5. Okay, you can't see my cursor.
wait. No, sir, I'm not able to see your question. Wait, wait.
You won't be able to see my cursor.
No, sir. I'm using mine.
So can you put this link in the chat? The link for this graph.
Okay, so okay, so okay.
Yeah.
I've said so.
So now you can see.
Yes, sir.
Yeah. So what I was saying is, so this value is your 10 is to power 2,
Yeah.
and this value is your 10 is to power 3, which is 10 times 10 into 10 is to power 2.
Yes, sir.
So in the between will be this value will be a 2 into 10 to the power 2, 3 into 10 to the power 2, 4 into 10 to the power 2, such that here you come 9 into 10 to the power 2, and this is your 10 into 10 to the power 2.
Yes, sir.
Similarly, here this value is your 10 into 10 to the power 3.
Yes,
This
sir.
value is your 1 into 10 to the power 3. So this similarly, this will be 2 into 10 to the power 3, 3 into 10 to the power 3, 4 into 10 to the power 3, such that. So now you can calculate what is this value.
So it is 4 into 10 to power 5.
Yes. So that will be your cutoff frequency. And from that you can calculate the delay.
So delay is 1 by 2 pi into cutoff frequency, right?
Yes.
Okay. But 0.97. Okay, sir. But I also know, sir, that the cutoff frequency is where the delay of minus 3 dB from the maximum gain.
gain is 1.
So that I think minus 3 dB, right? That's confused me, sir. That I which one I will use? Minus 3 dB point. That is from 20. Wait. From here it is 20 dB, right? From there is a downfall of minus 3 dB. It will be right. I think there, right, sir?
Right? But your that is minus 3 dB is your root 2. If you are
Yeah.
1 by root 2, minus 3 dB means 1 by root 2.
Yes, sir.
But cutoff frequency for transistor you have studied in class, it is equal to 1. Like when gain is 1.
Yeah.
So you use that value.
Okay, sir. Sir, what is a small signal gain?
Small signal gain as in
That is, it depends on early voltage and transconductance.
so you see uh, in your output curve. Initially there's a linear region and then there's a saturation region.
Yes, sir.
So if your transistor is operating in the linear region, that such that it is so small that it is not saturating.
Yeah.
It is in the linear region, so that region is called your small signal region, and the gain that you get there is your small signal gain.
So, which BJT it will be for high for?
What?
I mean, so there is a two BJT A and B. So for which one the small signal gain will be high?
Uh, I think the one with the higher early voltage should be. What we haven't studied part, so I'm not able to answer
Okay.
that.
Okay, sir. Can you see that the formula which sir taught us is 1 minus WBN square upon 2 ln square for base transfer factor.
Okay, so if you use this formula, you are getting the correct answer, right?
But I'm getting different values. That is, I got 0.87, but from your formula I got 0.9. Both options are there in the question, sir.
Yeah, but I told you, right? The exam will be set according to the formulas that are in the lecture videos. I am not setting the exam, right? I am not setting the
Yeah.
assignment questions or the exam questions that are being set by the professor. So he will be setting according to the formulas that he has taught in his lecture videos.
Okay, sir.
So use the formula that you have got from the lecture video, which is this formula.
Okay, sir. So ln is coefficient into lifetime, right? Under root of coefficient into lifetime, right?
Yes, ln is under root dn into tau
Yeah.
for a semiconductor.
Okay, sir. So in HGT, that is heterojunction, we use a material for the emitter, right?
Not necessarily. You can. So
Yeah.
heterojunction means your P side and N side are different materials.
Oh,
Like which generally we use silicon for both side. Both
yes.
P side semiconductor and N side semiconductor are silicon. So in a heterojunction, your one of the sides will be a different material. So it can be a different semiconductor or it can be a metal. So like you can,
Okay, sir.
instead of silicon you can use germanium. So germanium will have a higher band gap, so it has a more doping potential.
Yeah. Thank you, sir.